Welcome to my video lecture based on Electrical Machine 2, paper code ECEE 501. This paper is based on mark-out curriculum. In this lecture, we will highlight about synchronous machine equivalent circuit. In my previous lecture, I have discussed about synchronous machines principle, how synchronous machine can be operated as a generator or motor, where synchronous machine can be applied actually, how the synchronization process can be occurred, and how the synchronous machine can connect with infinite bus. That part I have briefly discussed in my last lecture. In this lecture, I will mainly discuss about equivalent circuit of synchronous machine. What is equivalent circuit? Basically, when we will construct a machine, the machine can be transformer, that machine can be induction motor, the machine may be DC machines. But what is the meaning of equivalent circuit? Equivalent circuit means it is the electrical equivalence of that particular machine. Basically, in any kind of machines, like any kind of motor or generator, it has two parts. One is stator side, another side is rotor side. And in equivalent circuit, we will not exactly make the stator like it is a mechanical construction, or we will not make the mechanical construction of motor. No, not. We will make the electrical equivalence of that machine, where we will just indicate how much voltage we are giving, or how much current is flowing, and how is the machine actually react when this voltage or current passes through its windings. And definitely that equivalent circuit will maintain the principle of that particular machine. So equivalent circuit means it is the electrical equivalence of the particular machine. So here we will take the equivalent circuit of synchronous machine. Myself, Rumlum Banerjee, Assistant Professor of Electrical Engineering Department, Dr. Sudhir Chandrasur Institute of Technology and Sports Complex. Formerly it was known as Dr. Sudhir Chandrasur Degree Engineering College. And this institute is under JIS group. So here we will start with equivalent circuit part phase construction. What is the meaning of part phase? Basically, synchronous machine is a three-phase machine. So when we are drawing the equivalent circuit, we will draw its part phase. That means if we have three phases like A, B and C, three phases are there, we will consider only one phase at a time. Suppose we are considering the phase A. Why we are considering only one phase? Because three phases have the same nature. Definitely these phases are 120 degrees apart from each other, but the output of these phases are similar. So if we just analyze the equivalent circuit of a particular phase A, then definitely the equivalent circuit of B phase will be also similar. C phase will be also similar. So definitely when we are considering a three-phase synchronous machine or three-phase induction machine, we are always drawing the equivalent circuit part phase. So see, this is the equivalent circuit at no load condition. What is the meaning of no load? That means at output side there is no load. So the load part here, it is open. You can see that switch is open in nature. So this is open circuit. That means load is not connected here. That means whatever amount of EMF is generated here, that much of output voltage we are getting. That means the value of the EMF, field EMF, it is nearly equal to the output voltage at no load condition. So, our voltage equations or output voltage equation will be ER minus IARA minus JIA XAL. At loaded condition, the flux per pole does not phi A, it becomes phi R, and induced EMF is no longer EF, it becomes ER. ER is basically the resultant EMF and RA is equals to the resistance and XAL equals to the leakage reactance. So definitely the resultant EMF equals to V plus IARA plus JIA XAL. Okay. Whereas in case of no load, the EMF equation or voltage equation is V equals to ER or EF. It is almost equal to the same value of EF or V is same, but no load condition. Okay. So for loaded condition, our output voltage V equals to ER minus IARA minus JIA XAL, where XAL is the leakage reactance. Okay. See what happens when the load is connected here, then IA current is flowing. IA current flowing means here IARA drop will be there, here IAXL drop will be there, and it will be output voltage is V. So definitely our input voltage or input EMF is ER equals to IARA plus IAJXAL plus V. Now this is the resultant EMF, which is combination of V plus IARA plus JIAXL. Now we are imagining that the difference in EF, that is the field excitation or EMF in field, and ER are because of reactance drop JIARAR. So we will consider excitation voltage or EMF with its internal leakage reactance, that is armature reaction reactance. So we are replacing that EF, this is the voltage JIA, JXAR and RA plus XAL, where JXAR, this is the armature reaction reactance drop. So our new equivalent circuit becomes, with considering armature reaction reactance drop, it becomes ER equals to V plus IARA plus JXAL IA, where EF equals to ER plus JIA XAR. So XAR equals to armature reaction reactance, XAL leakage reactance per phase, RA is the armature resistance per phase, XAL plus XAR is basically XA. So we are considering that XAL plus XAR, these two reactances are basically XAs, that is synchronous reactance per phase, which are totally called as synchronous reactance per phase. And definitely XAL is very greater than XAL. That is very large compared to XAL. Therefore, the equivalent circuit of synchronous machine per phase, now it will be EF RA J XS, where XS is summation of XAL plus XAR. So, our KVL equation is, it becomes EF equals to V plus IARA plus IAJXS, where ZS is basically RA plus JXS, where it is synchronous impedance, where XS very greater than RA. So, the synchronous impedance ZS is basically a fictitious impedance considered to account for voltage effects in armature circuit produced by actual armature resistance, leakage reactance and change in air gap flux caused by armature reaction. Okay, so you have to remember that this synchronous impedance ZS is basically a fictitious impedance which is considered to account for voltage effects in armature circuit produced by actual armature resistance, leakage reactance and change in air gap flux caused due to armature reactance. So, this is the basic fact. Now, these are the phasor diagram. Let us consider. This is our voltage. This is V. And this is the field EMF EF, and this is the flux, which is phi R is the resultant flux and phi F is the field flux. So, and this is the current IA, and in parallel to IA we will draw IARA drop. And definitely IAJXL, it is inductive drop, so definitely it will be line to TV lag. So, it is placed here and combination of these three is basically EF. We know from the equivalent circuit KVL equation, that is ER equals to V plus IARA plus JIAXL. Here it is this equation, EF equals to V plus IARA plus JXS, where XS is XAL plus XAR. So, here it is combination of XAL plus XAR. Combining both, it is basically JIAXS. Okay. So, in that way, we have drawn it. This is for the equivalent circuit. Now, let us consider a mathematical problem. So, this is related to equivalent circuit. A 300 MVA 11 kV 50 Hz star connected synchronous generator circulates a short circuit current of 700 ampere in the armature with field current of 15 ampere. The open circuit voltage is 1200 volt with the same field current. If the generator supplies a load of 3.5 kA at 0.8 power factor lagging, determine A. Power developed by the generator, B. Maximum power that can be developed, C. The power angle if the generator develops 150 megawatt for the same condition. So, we will solve this problem. So, neglecting the armature resistance, our XS is basically ZS. So, it will be definitely 1200 volt is the supply voltage. This is the open circuit voltage divided by root 3 into 700 ampere, the short circuit current. That means V by I is basically Z. And as this is star connected, so we have to divide it by root 3. So excess we are getting, that is 0.99 ohm. Now at 0.8 power factor, we know that E equals to root over 11 by root 3, that is, this is 11 kV. So it is 11 by root 3 into 0.8, that is the power factor lagging, plus 11 by root 3 sine alpha plus 3.5 into 0.99, that is whole square. So in that way we can calculate the EMF and the power developed, that is root 3 VI cos phi. So here it will be 53.35 megawatt, and maximum power developed, that is 3 into EV by XS. So the value is 3 into 8.87 into 11 by root 3 the whole divided by 0.99. The value of XS we have already calculated. So we are getting the maximum power developed in this case is 170.7 megawatt. So here all these working formulas, these things we will discuss in my next lecture, but here I am just point out the problem which generally comes related with synchronous machine. Now if the power factor angle is delta, so we will calculate the angle delta, that is by using this one, 150 equals to 3 into 8.87 into 11 by root 3 sine delta divided by 0.99. Okay, so that is 3 EV by XS sine delta is basically 150. Okay, because in this case the power angle, if the generator developed 150 megawatt, the output power developed in this case is 150. So for this case we are getting that the power angle is 61.49. So this is the simplest and small problem related to synchronous machine. In this lecture we have mainly highlighted about equivalent circuit of synchronous machine, and in my next lecture we will talk about the armature reaction of synchronous machine and the armature circuit voltage drop, salient pole induction machine, two reaction theory concept. Those things we will discuss in my next lecture. So thank you all for listening my lecture.